This is an A-level AQA chemistry question based around the topic of structural determination. Have a look at each section, read it carefully, see what you can do on paper, pausing as you go, and then review your answers by following the rest of the video. So here's part A. Part B. Part C. Part D. Part E, and finally Part F. Big question, total of 17 marks available. So let's go back to Part A, and we've got here something that is in common with proton NMR and carbon-13 NMR. And we use a compound that's used as the standard when recording a carbon-13 NMR spectrum, and it is used in proton NMR as well. Now, you simply have got to remember this. You need to know the name of it, you need to know the structure of it, and then you need to read the question carefully, because this very specifically says the skeletal formula. And what we want is SiCH3,4. So each of those sticks is going to a CH3, and the name for this is tetramethylsilane. We move on to part B. We've got 4 isomers of C6H12O2 analysed by carbon-13 NMR. The carbon-13 NMR spectra of 3 of these isomers are shown in figure 2. We want to know which of these spectra relate to which of the compounds. So the first thing that I've done is gone through to look at the carbon environments. I've used a different colour per environment within each structure, and remember that symmetry greatly reduces environments. You can see this in R and S, where I've got 3 CH3s all coming off the same carbon. That does mean that they are all equivalent hydrogens and equivalent carbons, and that's really important. But if I break that down a little further, you can see that P has 6 peaks, Q has 5 peaks, R and S have 4 peaks each. Now immediately I can go across and I can count my peaks, and I can see that there are 5 on the third spectrum. So that one is Q. I also know that there are none of these that have got 6 peaks, so I can immediately disregard P, and I know that my final 2 are going to be R and S. Now, to answer the next part, you have got to look at the datasheet, which gives you carbon-13 spectra chemical shifts. And you need to look at that table very carefully. Look for the carbons, look for the environments, and that's what's going to allow you to see that the top of figure 2 is S and the second is R. Moving on, we have got infrared spectra shown in figure 3 for the 3 different isomers T, U and V. Identify the functional groups present in each isomer, T, U and V, using table A. So once again, remember you are provided with a table of wave numbers for infrared spectra. So again, let's pick out the most important ones. If I look in the first isomer, T, I can see that I've got this really defined, pronounced, sharp peak, and it's around 1700. That fits with what we would always see with a carbonyl group. C double bond O, 1680 to 1750. Now, T has also got an OH stretch. OH is always characterised by this really broad peak over on the left-hand side. But depending on its position, it could tell us whether it's an alcohol or whether it's an acid. This is definitely in the 3230 to 3550 range, which tells us that it's an OH alcohol. So there's a really important distinction here for the third mark, because we know that there is an OH and we know that there is a C double bond O. But because we've not got an OH acid peak, we know that the OH and the CO are separate within the molecule. They're not coming off the same carbon, or the double bond O is not coming off the same carbon as the OH. And that was important to get the third marking point there. When I look at U, U has also very characteristically got the broad OH peak, and it's in the region of 3230 and 3550. But again, we've got to consider something really quite important here, because we know there are two oxygens. Now, there is no C double bond O peak here. There's no sharp peak at 1680 to 1750. So if the only functional group that contains an O is the OH alcohol, our deduction is that there must be two OH peaks within this structure. And then for the final one, we have got an OH broad peak once again, but this time it is in the region 2,500 to 3,000. And there is also the C double bond O peak at 1680 to 1750. So we can be confident that we have got a COOH bond. When I move on to part D, and we're starting to deal now with proton NMR, the integration values for the peaks in the 1H NMR spectrum, a different isomer of C6H12O2, the data is given in the table below. So we've got 5 different chemical shifts, each of them with an integration value, each of them with a different splitting pattern. So, first thing to do, deduce the simplest ratio of the relative numbers of protons in each environment. Remember, by protons, we mean hydrogens. So the first thing I'm going to do with the integration values is divide by smallest, and that's going to take me to a ratio of 1 to 1 to 1 to 1.5 to 1.5. I'm going to take a look at the fact that that would give us a total of 6 hydrogens. Actually, we've got 12 hydrogens. We know that from the structure. So I'm going to double all of those up. So my simplest ratio of relative numbers of protons is 2 to 2 to 2 to 3 to 3, taking us up to the total 12 hydrogens. And that's going to help us to start to build a structure as well. Moving on to part E. Using the data in the table above and table B in the data booklet, deduce the part of the structure of X that causes the signal at chemical shift 3.5 and the part of the structure at X that causes the shift at 2.2. Explain the splitting patterns of these peaks. So you might need to jump back and forth to re-look at the structures. But let's take a look. At 3.5, we've got a quartet. And it's next to the OCH2. Now, it's a quartet because there is an adjacent CH3 group. If I move on to the peak at 2.2, it's a singlet at 2.2. It's next to the C double bond O. We can see here that we've got a singlet because it has no neighbouring non-equivalent hydrogens. And as we can see there, that's worth a mark. So singlet because there are no adjacent protons. To answer a question like this, you've got to get yourself familiar with the chemical shift tables and to be able to use them. Moving on, and we have part F. Deduce the structure of the compound C6H12O2. Now, again, it's quite difficult unless you go back through the video, but essentially you've got lots of key pieces of information that you are going to build together so that we can see we have the correct number of proton environments. I've got here 1, 2, 3, 4, 5 environments. I can see that there's a 3, 2, 2, 2, 3 ratio of hydrogens, which fits in with an earlier question. We can look at the splitting patterns. These would give rise to a singlet because there are no neighbouring non-equivalents. These would give rise to a triplet because of the 2 neighbouring non-equivalents. These would give rise to a triplet because of the 2 neighbouring non-equivalents. And a CH2CH3 will often give rise to a triplet quartet. We have a quartet because of the neighbouring CH3 and a triplet because of the neighbouring CH2. So there's lots of information that's been pieced together to get to that answer. These are complex, these are complicated, and they get better with lots and lots of practice. That takes us to the end of this question. Thank you for listening.